Now, in this lecture, we're going to look at follow-up analyses to a significant Kruskal-Wallace test. Suppose that the Kruskal-Wallace test has been used to compare the locations of two or more populations and that the Kruskal-Wallace test is significant. Now, are we done? Do we stop there? Absolutely not. The Kruskal-Wallace test is not the end of the analysis, but rather just the beginning. If the null hypothesis of the Kruskal-Wallace test, that is, that all populations are the same in every way, and in particular with respect to location, has been rejected, and it has been concluded that differences in location exist among the populations, then the natural and immediate follow-up question is this: where do the differences lie? Which populations are different from each other? Now, if you'll think back to your first methods class, when you covered analysis of variance, this is the same approach that we use there. The only difference is that was a parametric type of environment. This is a non-parametric situation. But the underlying questions are still the same. If we conclude that populations differ, then we want to know which populations are different, and if we can find out more than that, to what extent do they differ? So this is the question we're going to consider in this section. So again, the null hypothesis being tested by the Kruskal-Wallace test is the following. And I'll denote it this way using this fairly loose notation like we talked about before. So the null hypothesis is that the population means, the K population means, are all the same, against the alternative that differences exist among the populations, and in particular with respect to their locations. Now, one approach to follow-up testing is to perform pairwise comparisons. So this is how we would represent a given pairwise comparison. So the null hypothesis would be that population I is the same as population J against the alternative that the two populations are different for all indices I not equal to J. Now, how many comparisons are we going to have to make? There are K choose 2 pairwise comparisons that we'll need to perform in order to answer these questions fully. Okay, so let's look at the procedure. So we're going to specify the hypotheses. In this context where we are comparing multiple populations with the Kruskal-Wallace and then drilling down if that test is significant and doing pairwise comparisons, our primary interest is going to be on two-sided tests. That's all we're going to look at in this section is two-sided pairwise tests. So the null hypothesis would be that population I is the same as population J against the alternative that the two populations, population I and population J, are different. And again, we're going to do this for all I not equal to J. The test statistic is given here. If you look at it, this looks very much like the test statistic for a two-sample t-test. It's very similar. In fact, we're actually going to call this test statistic t-calc. And the reason is the reference distribution for this test is the student's t-distribution. Now, I'll just say that that's not the exact sampling distribution of this test statistic. It's a large sample approximation to it. If you think back to some of the nonparametric tests that we've looked at so far in this class, one good example would be the Kruskal-Wallace. Another one would be the Mann-Whitney test. We looked at large sample approximations to those exact tests. And that is also what we're doing here. We are going to be utilizing a large sample approximation to perform this test. So the quantities in the numerator, the t-bar I and t-bar J, those are the average ranks for samples I and J. Now, down in the denominator, we have S squared and we have H. And those two quantities were computed in performing the original Kruskal-Wallace test. So once we've gotten this far in the process, we've already done the Kruskal-Wallace test, and so we'll already have S squared and H. Okay, now we also have N without a subscript, and we have K. Now remember, N is the total sample size, and then K is the number of groups or the number of populations overall that we compared in the context of the Kruskal-Wallace test. So this is the test statistic that we're going to be using, and we have to be able to evaluate the value from the test statistic, and so that requires us to come up with our rejection criteria. And so for a significance level of alpha, we're going to reject the null hypothesis if our test statistic t-calc is either really small or if it's really big. And the reason is, again, because this is a two-sided test. The alternative says that population I is not equal to population J. That's a two-sided alternative. And so we're going to reject the null hypothesis if our test statistic t-calc is either really small or if it's really big. Now remember that I said that the reference distribution is students' t-distribution, and in particular it's students' t-distribution with degrees of freedom equal to n minus k, where again n is the total number of observations and k is the number of groups. Also, because this is a two-sided test, the p-value of the test is 2 times the probability that a t-random variable with n minus k degrees of freedom is greater than or equal to the absolute value of the test statistic. Now again, this also should look very familiar to you. This is the same formula calculating the p-value for a two-tailed t-test that you learned back in your first methods class. The only difference here is in the number of degrees of freedom. For a one population or one sample t-test, the number of degrees of freedom is n minus 1, but in this case we're comparing k populations, the degrees of freedom are n minus k. So that is the procedure. We've got the hypotheses that we're going to be testing for each pairwise comparison. We have the test statistic that we're going to be calculating, that we're going to be using to perform the pairwise comparison. We have the rejection criteria that we're going to be using to evaluate the value of the test statistic. And then we have a formula that we may be able to use to calculate the p-value depending upon the tool that we have for calculating this probability. Even with a t-table, we can come up with an approximation to the p-value using this formula. Okay, so let's look at some examples of this. So this will be example 3.7. Now this is a continuation of example 3.4 that we looked at previously, where we were comparing 3 methods of teaching a foreign language to young kids. Alright, so in example 3.4, the Kruskal-Wallace test was used to compare 3 methods of teaching a foreign language to children 6 years of age. In that example, it was concluded at the 0.05 level of significance that differences do exist among the 3 teaching methods in terms of their effectiveness. A natural and immediate follow-up question is this: if the populations are different, where do the differences lie? Which populations are different from each other? In the original in the original Kruskal-Wallace test, we compared 3 methods or 3 populations. And so to perform a complete analysis and answer all of these questions, we'll have to do 3 choose 2 or 3 pairwise comparisons. All right, now in the original Kruskal-Wallace, we calculated the ranks of the observations for each sample. And remember the way we did that. We put all the samples together into one big sample and ranked the observations in that combined sample. And then once we had the ranks, we separated those ranks back into the original samples. So that's what I've got represented here. We've got 3 samples, 1 from each teaching method. I've also included over here on the far right-hand side the rank sum for each sample and the average rank for each sample. The rank sum, the sum of the ranks for each sample, were used in performing the Kruskal-Wallace test. What we're going to find, and what we've actually already seen in terms of the setup or the procedure, is that when we drill down and start doing pairwise comparisons, we're going to be using the average ranks. So these are the values that we'll use in performing the pairwise comparisons. So for example, T1 bar is 16.64, T2 bar is 10.25, and T3 bar is 5.42. Okay, so just a few values from the original analysis, the original Kruskal-Wallace analysis that we'll need going forward. We've got the sample sizes, so N1 is 7, N2 is 8, and 3 is 6. And then we also need S squared and H. So S squared was calculated in performing the original Kruskal-Wallace test, and it was 38.4. And then the ultimate test statistic that we used, that we calculated for the Kruskal-Wallace test, was 10.7926. Okay, so there are 3 pairwise comparisons that we're going to perform in order to answer the question which populations are different from each other. And so the first comparison is a comparison of methods 1 and 2. And so the null hypothesis to be tested is that population 1 is equal to population 2. The alternative is that population 1 is not equal to population 2. We could also express this as method 1 equal to method 2 for the null, and method 1 not equal to method 2 for the alternative. All right, but you understand what this represents. We're wanting to compare these methods, and the populations that we're talking about here are the populations of scores that students obtain under the various methods. Okay, the significance level we're going to use is 0.05, and the degrees of freedom for the test That is given by n minus k. N is the total sample size, the total number of observations, that's 21. And we're comparing 3 populations overall, and so k is equal to 3. And so this test has associated with it 18 degrees of freedom. The formula for the test statistic is given here. So again, we're going to call it t-calc to help remind us that we go to the t-table to get the critical points. The numerator is t1 bar minus t2 bar. And then we have the estimated standard error of t1 bar minus t2 bar. S squared is obtained from the original Kruskal-Wallace. We had that listed on the previous slide. We also need h, which is the test statistic from the Kruskal-Wallace test. And notice that in the denominator, the only quantities that are indexed or subscripted are the sample sizes down here. So as we go from one pairwise comparison to another, in the denominator, these are the only values that could potentially change. Now, if all sample sizes are equal, then this won't change from one pairwise comparison to another. But as is the case in this example, we've got different sample sizes, so we need to be careful that we plug in the correct values there. Okay, the reference distribution is the t-distribution with 18 degrees of freedom. And if we look up the upper 2.5 percentage point of the t-distribution with 18 degrees of freedom, we see that that's equal to 2.101. So the lower critical point, right, is negative 2.101, and the upper critical point is positive 2.101. Okay, then we plug in the quantities that we need to calculate the test statistic. And so we are grabbing these values from the table. Let me just scroll back here quickly. Okay, so these are the average ranks, and we're comparing methods 1 and 2. And so we get these average ranks for the corresponding samples. And then the value for S squared from the original Kruskal-Wallace test was 38.4. The value of H in the Kruskal-Wallace was 10.7926. Sample 1 has 7 observations. Sample 2 has 8 observations. All right, so we plug all those values in, and we get a test statistic equal to 2.785. Since 2.785 is greater than the upper critical point, the rejection criteria have been met, and so therefore we're going to reject the null hypothesis. And so we can say that there is sufficient evidence at the 0.05 level of significance to conclude that method 1 and method 2 differ in their effectiveness in teaching a foreign language to children 6 years of age. The last thing I want to say about this particular comparison is that based on the value of the test statistic, 2.785, and if we look up in the row in the t-table for corresponding to 18 degrees of freedom, we're going to be able to tell that the p-value is between 0.01 and 0.02. Okay, the next comparison is to compare methods 1 and 3. All right, and so the null hypothesis is that population 1 is equal to population 3 against the alternative that population 1 is not equal to population 3. Again, we're going to perform this test at the 0.05 level of significance, and it's an 18 degree of freedom test. All right, I like to make sure that I write down the formula for the test statistic just to make sure I plug in the correct values. And so anyway, we're comparing methods 1 and 3. So we've got t-bar 1 and t-bar 3 in the numerator. And again, the only place downstairs that's going to change is in the sample sizes. So I've got that reflected right here. So that's the formula for the test statistic. We've got the same exact rejection criteria. So we're not going to spend any time again looking at this, but we've got the same exact rejection criteria. And so now all that's left is to calculate the value of the test statistic and then evaluate it using the rejection criteria and then draw a conclusion. So in this case, for this comparison, the numerator is going to be 16.64 minus the 5.42. Then we have to calculate the denominator and divide that into the difference. And that turns out to be 4.550. And so since that exceeds the upper critical point, again, the rejection criteria have been met. And so therefore we reject the null hypothesis. So we can say there is sufficient evidence at the 0.05 level of significance to conclude that method 1 and method 2 differ in their effectiveness in teaching a foreign language to children 6 years of age. Finally, we can tell from the value of that test statistic and also the t-table, we can tell that that p-value is less than 0.001. Okay, and finally, the last pairwise comparison, we're going to compare methods 2 and 3. So the null hypothesis is that populations 2 and 3 are the same, against the alternative that population 2 is not equal to population 3. Again, we're going to use a 0.05 level of significance. The degrees of freedom for the test are 18. The formula for the test statistic is given by this expression, so it has the same format, but again, we have to make sure that we include here the appropriate methods or samples that we're going to be using, so t-bar 2 and t-bar 3. And again, that's reflected down here in the sample sizes. So just be careful when you make those calculations, that you're making sure to plug in the correct values. Okay, so then we have the same rejection criteria, right? So nothing changes there. And we plug in t-bar 2 and t-bar 3 into the numerator, and then the corresponding sample size is down below, and we get a test statistic of 2.018. So since the test statistic 2.018 is not less than negative 2.101 and 2.018 is not greater than the upper critical point, the rejection criteria have not been met, and so therefore we fail to reject the null hypothesis. And so we can conclude that there is insufficient evidence at the 0.05 level of significance to conclude that methods 2 and 3, I've got a typo there, let me change that. So there's insufficient evidence at the 0.05 level of significance to conclude that method 2 and method 3 differ in terms of their effectiveness in teaching a foreign language to children 6 years of age. And we can note from the t-table that the p-value is greater than 0.05, strictly greater than 0.05, but less than 0.10. So the comparison here is approaching significance at the 0.05 level, but it's not quite there. Okay, so what can we conclude? We did the overall Kruskal-Wallace. We concluded that differences existed among the methods in terms of their effectiveness in teaching a foreign language. Then we drilled down and we're looking at pairwise comparisons. We've concluded that method 1 is different than method 2, method 1 is different than method 3, but methods 2 and 3 are not different. All right, and so I think that you would agree that we can conclude, if I scroll back up here, in looking at those average ranks, what we're concluding here is that method 1 is actually the best of 3, and that there's not a significant difference between methods 2 and 3. So if we had to choose a method, we would want to choose method 1. Okay, so that is the end of example 3.7, and I think it shows you this process that you're going to be using as you perform non-parametric comparisons of populations using the Kruskal-Wallace test. The Kruskal-Wallace test is just the start of the process. It's not the end of the process. If you decide that, well, I suppose we would say that if you conclude that there are no differences using the Kruskal-Wallace test, then you stop there. There's no sense in drilling down. In fact, you would not want to. But if you do conclude based on the data, based on the evidence, that differences do exist, then it makes sense. It's just a natural follow-up to find out where those differences are, and we do that by performing these pairwise comparisons. All right, now the next example, this is example 3.8, and this is a continuation of example 3.5. In that example, we compared the lifetimes of 4 brands of automobile tires. We're going to follow up that analysis with some pairwise comparisons. So in example 3.5, the Kruskal-Wallace test was used to compare the lifetimes of 4 brands of automobile tires. In that example, it was concluded at the 0.05 level of significance. The differences do in fact exist in the lifetimes of the 4 tire brands. So the natural and immediate follow-up question is, which brands differ? Now, with 4 tire brands overall that we're comparing, to perform all pairwise comparisons, we've got to compare 4, choose 2, or 6 pairwise comparisons. Okay, so the table below contains the ranks along with the rank sum and the average of the ranks for each brand. Now, for this follow-up procedure, I'm providing a little more precision in terms of the average ranks than I did when we did the Kruskal-Wallace test, just to get a little bit more precise result. Okay, so these are the ranks for the 4 brands, and again, we've got the rank sum, the sum of the ranks within each sample, and the average rank within each sample. And so some summary statistics from the original analysis that we'll need. In this case, the sample sizes are all the same. Right? We had 6 automobiles using each of the tire brands. So the total sample size is 24. From the original Kruskal-Wallace test, the value for S squared was 38.4, and the value for H was at 10.7926. Actually, that's a carryover from the previous example. Let me fix that real quick, so hold on just a second. All right, so I've got the slide corrected here. So actually for this, for the original Kruskal-Wallace for this data, the value of S squared was 49.6957, and the value of H was 8.4682. So the perils of cut and paste. Okay, so again, there are 6 pairwise comparisons, and so a little bit more work to do because we've got more populations that we're comparing from the start. The first pairwise comparison is a comparison of brands 1 and 2. So we've got this two-sided test comparing populations 1 and 2. We're going to perform the test at the 0.05 level of significance, and the degrees of freedom associated with the test is 20. The total sample size of 24 minus the number of groups or populations that we're comparing. So this is a 20 degree of freedom test. The test statistic is given here. All right, we've seen that, so I'll just move along here. Now, again, the reference distribution is the t-distribution with 20 degrees of freedom. The upper 2.5 percentage point of that distribution is 2.086, and so the lower critical point is negative 2.086, and the upper critical point is positive 2.086. Now, the value of the test statistic turns out to be 0.0478. Let me just go back to the slide with the average ranks. If you look at those values, we're going to be using these values to help us decide which brands are different. And you can see here that the average ranks for brands A and B are very, very similar. So we might just, by looking at this, conclude, initially at least, that those 2 brands are not different. But they are different than some of the others. So we can see here that the value of this test statistic is very small, and we would expect that because this difference is not very big. It's pretty small. Okay, so since the value of the test statistic, 0.0478, is not less than negative 2.086, and it's not greater than positive 2.086, the rejection criteria have not been met. Therefore, we fail to reject the null hypothesis. And so there is insufficient evidence at the 0.05 level of significance to conclude that a difference exists in the lifetimes of tire brands 1 and 2. Now, from the t-table, we can tell that the p-value for this test exceeds 0.5. Okay, the second pairwise comparison is a comparison of brands 1 and 3. And so we've got the appropriate two-sided test here for the hypotheses. We're going to perform this at a significance level of 0.05. And again, it's going to be a 20 degree of freedom test. Okay, we have the appropriate formula for the test statistic here. And then we've got the same rejection criteria. So all we have to do is calculate the value of the test statistic. And so the test statistic for comparing brands 1 and 3 is 1.1048. And since that is not less than the lower critical point and it's not greater than the upper critical point, we fail to reject the null hypothesis. There is insufficient evidence at the 0.05 level of significance to conclude that a difference exists in the lifetimes of tire brands 1 and 3. Finally, we can approximate the p-value using the t-table and see that the true p-value is between 0.2 and 0.5. The third pairwise comparison is comparison of brands 1 and 4. And so we have the appropriate formula for the test statistic. We utilize the same rejection criteria. And the test statistic for this comparison is 2.9784. And that's certainly larger than the upper critical point. And so the rejection criteria have been met. And so therefore we do reject the null hypothesis. And so we can say that there is sufficient evidence at the 0.05 level of significance to conclude that a difference does exist in the lifetimes of tire brands 1 and 4. And also note that we can conclude that the p-value is greater than 0.002 and less than 0.01. So not only would we reject at the 0.05 level, we can see that we would reject at the 0.01 level as well. So there's strong evidence. A difference exists in the lifetimes of tire brands 1 and 4. Okay, the next pairwise comparison is a comparison of brands 2 and 3. So I've got the hypotheses laid out here. I've got the formula for the test statistic that I'm going to use. We're going to use the same rejection criteria, aren't we? And then we plug in the value for the test statistic. And so for this comparison, the test statistic is 1.0570. That is not less than the lower critical point, and it's not greater than the upper critical point. And so the rejection criteria have not been met. and so we fail to reject the null hypothesis. There is insufficient evidence at the 0.05 level of significance to conclude that a difference exists in the lifetimes of tire brands 2 and 3. Based on the value of the test statistic and also the t-table, we can tell that the p-value for this test is actually between 0.2 and 0.5. So because the p-value, for example, is greater than 0.2, we would not reject the null hypothesis at the 0.1 level, not even at the 0.2 level. The fifth comparison is a comparison of brands 2 and 4. All right, so I've got the hypotheses specified here. All right, I've got the formula that I'll use for the test statistic, same rejection criteria, and then we calculate the value of the test statistic. So what we have here, a value of 2.9306 for the test statistic, and since that value exceeds the upper critical point, the rejection criteria have been met, and so therefore we do reject the null hypothesis. We can say there is sufficient evidence at the 0.05 level of significance to conclude that a difference exists in the lifetimes of tire brands 2 and 4. And finally, we can discern from the t-table and the value of the test statistic that the p-value for the test is greater than 0.002 and strictly less than 0.01. And so from that we can see that we would not only reject at the 0.05 level, but we would reject at the 0.01 level of significance as well. Finally, our last comparison, a comparison of brands 3 and 4. So I've got the pairwise comparison hypotheses specified, and we've got the formula specified here. We'll use the same rejection criteria. All right, so then we evaluate the value of the test statistic. Since that is not less than negative 2.086 and it's not greater than the upper critical point of positive 2.086, again, the rejection criteria have not been met, and so therefore we fail to reject the null hypothesis. So there is insufficient evidence at the 0.05 level of significance to conclude that a difference exists in the lifetimes of tire brands 3 and 4. And then finally, note that the p-value for this test is something greater than 0.05, but less than 0.10. And so when we put all this together, what have we concluded? Well, there's not a significant difference between tire brands 1, 2, and 3, but tire brands 1 and 2 are significantly different from 4, but tire brand 3 is not different than 4. Anyway, and this is the same kind of breakdown in the analysis, breaking down of a problem into its component pieces once we reject that initial Kruskal-Wallace test, just in the same way that we, if we have a significant ANOVA, we look at pairwise comparisons to find out where those differences are. We've done the same thing here. All right. So that is the end of this example, and it's the end of this particular lecture video. So I hope you find that useful. Now remember that the Kruskal-Wallace test, it's just the start of a set of analyses. Obviously, if we fail to reject the null hypothesis of the Kruskal-Wallace test, then there's no point in proceeding with pairwise comparisons because we've not concluded that differences do exist. But if we do reject that null hypothesis and have concluded therefore that differences do exist, then it makes sense, right? And it's just a natural follow-up question, where do those differences lie? And that is what these pairwise comparisons allow us to answer.